3. Measuring brightness. The power rating of a lamp tells us how much power it consumes, but not the output power of the lamp. Theoretically, we can measure the power output of EM wave produced by a lamp, but it includes also the invisible spectrum. We may also measure only the power of visible light it produces, and yet it is still not good enough. Why? Brightness is in fact a subjective measurement. Our eyes are more sensitive to yellow-green light. The chart below shows that for the same power output, the brightness of a 555 nanometer source is about double that of a 610 nanometer source. A. Luminous flux. Luminous flux is a measure of light power, taking into account the sensitivity of human eyes to different wavelengths of light. In other words, it is a measure of visible power. Strictly speaking, luminous flux is the power output of a light source corrected for the dependency on the wavelength of the human eye. So, not only the output power of visible light may affect the measured luminous flux. In other words, luminous flux is something just like visible power. The unit of luminous flux is lumen, abbreviated as Lm. In particular, a 555 nanometer source with an output power of 1 watt produces a luminous flux of 683 lumen. For the same source, if the output power is doubled, in other words, a 555 nanometer source with an output power of 2 watt produces double the luminous flux, which is 683 multiplied with 2 lumen. A 610 nanometer source with an output power of 2 watts produces a luminous flux of 683 lumen. And a 4 watt output produces a luminous flux of 1366 lumen. For a 500 nanometer light source with an output power of 1 watt, it produces a luminous flux of 683 divided by 3, which is 227.7 lumen. So, a 500 nanometer source with an output power of 3 watts produces a luminous flux of 683 lumen. Let's compare the luminous flux of the following 2 light bulbs. For the one on the left, it produces 472 lumen of luminous flux. And for the incandescent lamp on the right, it produces a luminous flux of 400 lumen only. B. Illuminance. While luminous flux is a measure of total visible power of a light source, illuminance measures the visible power as received per unit area, which is a more appropriate measurement of brightness. Experimentally, we may use a light meter to measure illuminance at a certain distance from a light source. Let's take a look of the following experiment.
In this experiment, we will measure the brightness of a lamp using a light meter. A 100-watt lamp is placed at about 1 meter away from a light meter. Adjust the receptor of the light meter so that it faces the lamp normally. Black out the laboratory to ensure the light meter receives only the light from the lamp. Select the appropriate range of operation for the light meter. Record the reading of the light meter. This is the illuminance measured at the position of the light meter. Can you estimate the luminance flux of the lamp according to the results of this experiment?
In physics, intensity measures power per unit area, while luminous flux measures something like visible power. Illuminance measures something like visible intensity. Compare the following relationships. Intensity equals power over area, and that from your book, illuminance equals luminous flux over area. They look pretty alike, right? Illuminance is measured in lux, abbreviated as Lx, where 1 Lx equals 1 lumen per meter square. Also note that luminous flux measures the effective visible power of a source, while illuminance measures the effective visible intensity received by a surface. You may visualize luminous flux as light energy flux lines produced from the source, as it is found on page 49. C. Lambert's cosine law. When luminous flux phi hits a surface at right angle, the illuminance is given by E equals phi over A. When the luminous flux phi hits the surface at an angle theta, the illuminance is reduced as the light energy spreads in a larger area of A over cosine theta. The illuminance becomes E cosine theta. Example 1. The question by itself is straightforward. By the way, you should note that for a distant source or a nearby source with a large surface area, the luminous flux are considered to be parallel. On the other hand, a small source can also produce parallel flux by the use of converging lens, such as the light from the torch in this example. D. Inverse square law. For point source, on the other hand, the illuminance obeys inverse square law, as the luminous flux evenly distribute in all directions. The illuminance at a point facing the point source at a distance r is E equals phi over 4 pi r square, which means the illuminance E is inversely proportional to the square of distance r.
In this experiment, we will verify the inverse square relation between the illuminance at a point, due to a point source of light, and the distance from the source. Place a 100-watt lamp about 1 meter in front of the light meter. The receptor of the light meter should face the lamp normally and at the same height as the lamp. Switch on the lamp and the light meter. Black out the laboratory to ensure that the light meter receives only the light from the lamp. Record the light meter reading E and the distance R between the light meter and the lamp. Repeat the above steps with R gradually increasing. Find the values of 1 over r squared. Plot a graph of E against 1 over r squared. What conclusion can you draw from the graph?
What about the illuminance at point X? making an angle with the source as shown in figure 2.1ae. Using Lambert's law, the illuminance is given by E dash equals E cosine theta, which is phi cosine theta over 4 pi r square. By the way, a point source with perfect back reflector only illuminates a hemisphere. The illuminance at a point facing the source is given by E equals phi cosine theta over 2 pi r square, where r is the distance from the source. And what if the reflector is not perfect? Sounds difficult, right? So why not take a look at the following. Example 2. Finding illuminance. This is a straightforward application. First, the flux at A is perpendicular to the surface. The illuminance is given by E equals psi cosine 0 over 4 pi r square. B is much further away, and the flux makes an angle with the surface at B. Find the angle theta first, and apply the standard Lambert's law to find the illuminance A, which equals psi cosine theta over 4 pi r square, where theta equals arctangent 2 over 1. Exam length 1. Another expression of illuminance. Given the illuminance at x, you have to find the illuminance at y. First, you must find the angles made by the flux and the surface at the 2 points, which are 30 degrees and 40 degrees respectively for x and y. Second, the distance from x and y are different and are related by the angles again. The two different distances are expressed in terms of the length h and the angles at x and y. Lastly is a little bit of mathematics to relate the two illuminates, eventually expressed in terms of the angles. Do Chap.4 on the next page.